Open a viral video and look at the view count. Now refresh the page. The number just jumped by 4,000 in 2 seconds. Here is why that should bother you. No database on Earth took 4,000 writes to a single row that fast. The number you are watching climb was not read from a counter. So where did it come from? It was not stored anywhere. It was estimated. And once you see how, you cannot unsee it, because the same trick is hiding inside almost every large system you have ever used. At a certain scale, the giants quietly stopped counting things exactly, on purpose. This is how they fake a number you trust every single day. On one server, counting is the most boring problem there is. You keep a number. A view comes in, you add 1. Someone asks for the total, you read it back. A single integer in memory, and you are done. This works perfectly, and it keeps working perfectly, right up until 2 things happen at once. The whole difficulty in this video lives in that phrase, at once. The moment you have more than one machine adding to the same number, counting stops being arithmetic and becomes a coordination problem. So let us break it the way production breaks it, one layer at a time. The obvious first move is to put the count in a database. One row, one number, and every view runs an update. Set count equal to count plus 1. The database keeps those updates from corrupting each other, so the math stays correct. And for a long time, this is genuinely the right answer. The problem is contention. Every update wants to touch the same row, so to stay consistent, the database locks that row, applies your plus 1, then releases it for the next writer. 10 views a second, no problem. But a popular video gets 50,000. Now, 50,000 writers are lined up single file, waiting for one row. That row has a name. It is a hot row, and it will be the bottleneck for your entire service. And it is worse than one slow row, because a view is never just a view. A real view event fans out. The total on the video, this user's watch history, the creator's channel total, the trending numbers, the regional breakdown, the per-hour buckets that draw the graph in the studio dashboard. One human pressing play turns into a dozen numbers that all need to move. So 50,000 views per second is really hundreds of thousands of writes per second, everyone contending for some hot row somewhere. This is write amplification, and it is why you cannot simply throw a bigger database at the problem. The data is small. What overwhelms you is the rate of agreement, all those writers trying to move the same numbers at the same time. Here is the shift in mindset that defines the whole architecture. Stop trying to be correct at the instant of the view. When a view happens, do not update a total. Just write down that it happened. Append one small event to a durable log, immediately tell the user, got it, and move on. The view is now recorded. It simply has not been counted yet. This single decision is what every large counting system is built around. It splits the problem cleanly in two. Recording the event has to be fast and never lost. Counting the events is allowed to be slower and a little behind. Separating those two jobs is the whole game. The write stays simple, and all the hard work moves downstream where it has room to breathe. So let me define that pipeline concretely, because this is the part people gloss over. It has 5 stages, and real companies run real software at each one. Stage 1, ingest. Every view event is appended to a distributed commit log, almost always Apache Kafka, partitioned by video ID so all the events for one video land in order on the same shard. Kafka does not count anything. Its only job is to durably accept millions of events a second and hold them. Stage 2, stream processing. A job in Flink or Spark Streaming reads from Kafka continuously and does the actual aggregation, adding events up inside short time windows. Stage 3, the serving store. The stream job writes its running totals into a fast read store, Redis for the hot live numbers, Cassandra or a column store for the durable per video totals, and an analytics engine like Druid or ClickHouse for the slice and dice queries the creator dashboard runs. Stage 4, the read path. When you load the page, you never touch Kafka or Flink. You read one already computed number out of Redis or Cassandra in a millisecond. Stage 5, the batch layer, which we will come back to. Ingest, aggregate, serve, read, audit. That is the shape, at YouTube, at Twitter, at basically everyone. The clever math we are about to cover all lives inside Stage 2. So zoom into Stage 2, the stream processor, because adding up raw plays inside a time window is the easy half. One person hitting refresh 10 times is 10 plays, but one viewer. The number that actually matters is the second one, distinct people, and it is the expensive one, because to know if a viewer is new, you have to remember everyone you have already seen. Imagine a video with 800 million unique viewers. To count them exactly, you keep a set, a giant list of every viewer ID, and check each new viewer against it. 800 million IDs, several gigabytes of memory, for the count of one video held live in the streaming job. Multiply that across every popular video on the platform, and you would need more memory than the entire service has, just to count people. So exact counting is off the table. The way out is to stop demanding the precise number and accept a very close guess instead. This is where it gets almost unfair. A structure called hyperlog can count how many unique viewers you had from a few kilobytes. The same answer that needed gigabytes now fits in the space of a paragraph. The intuition is a coin-flipping game. If the most heads I ever got in a row was 2, you would guess I did not flip many times. If I once got 20 heads in a row, you know I was flipping for a very long time. Rare events imply a lot of trials. Hyperlog does exactly this. It hashes every viewer ID into what looks like a random string of bits, and it watches for rare patterns, like a long run of leading zeros. The rarest pattern it has ever seen tells it roughly how many different things streamed past. The viewers are thrown away. All it keeps is the high score of randomness. From a few kilobytes, it estimates 800 million unique viewers within about 2%. And here is why it fits the pipeline so perfectly. 2 of these sketches merge into one just by taking the bigger high score in each slot. So every shard of the stream job keeps its own sketch, and at the end, you merge them into the platform-wide unique count. Redis ships hyperlog as a built-in command, and it is exactly how large systems count uniques in production. Hyperlog answers how many unique people. A second component in the same stream job answers a different question: how many times have I seen each of millions of different things? Views per video, across every video on the platform, where new videos appear every second. Keeping an exact counter for each one is its own memory explosion, so the streaming job uses a cousin structure called a count min sketch. Picture a small grid of counters. Every time an event comes in for some item, you hash that item a few different ways, and each hash points at one cell in the grid. You bump those few cells. To read an item's count back, you look at the same cells and take the smallest one. Different items will sometimes collide into the same cell, so a cell can be pushed up by traffic that was not yours. That is why you take the minimum. It is the cell least polluted by collisions. The sketch can overcount, but it will never undercount, and you decide up front how much memory to spend to keep the error small. This is what powers things like the trending list and abuse detection, where you need a fast approximate count for millions of items, but you cannot afford a real counter for each. The third component sits earlier in the pipeline, right at ingest, and it is the bluntest move of all. When the fire hose is too big even for Kafka and Flink to swallow whole, do not record every event. Record 1 in 100 and multiply by 100. This sounds reckless, and at small numbers it is. But the magic of sampling is that the error shrinks as the count grows. For a video with 1,000 views, a 1% sample is noisy and useless, so you do not sample it, you count it exactly. For a video with 1 billion views, a 1% sample is 100 million measured events, and the estimate is tight to a fraction of a percent, which is exactly the right shape, because the videos with billions of views are precisely the ones whose exact count you can least afford to maintain. Big platforms sample the heavy hitters at the door and count the long tail exactly. You spend your effort where it is cheap, and you sample where it is expensive. Now we close the loop on stage 5. Everything so far has been the fast path, the speed layer, approximate by design. Running underneath it is a second path, the batch layer, and the classic name for running both together is a lambda architecture. The batch layer takes the same raw events, the complete log sitting in Kafka, and reprocesses all of them slowly and exactly. Its whole job is to be skeptical. Go back through every event, throw out the bots, the double counts, the replays that did not really happen, and produce a number it is willing to defend hours later. Then it overwrites the fast approximate number in the serving store with the audited one. Lambda is the classic shape, though many teams now collapse it into a single streaming path called a kappa architecture, where one exactly once pipeline does both jobs so there are not two code bases to keep in sync. Either way, The principle is the same: a fast approximate count for the experience and a slow exact count for the money and the trust. The number reconciles toward truth over time. It is never both fast and exact at the same instant because nothing at this scale ever is. This is also the real story behind a famous piece of internet folklore, the YouTube 301 freeze. The popular explanation is that some skeptical second system kicked in at exactly that number. The actual reason is simpler. Once a video passed a few hundred views, YouTube would freeze the public count and hold it while it checked those views for fraud and bot inflation before letting the number climb again. The freeze was the audit being slow on purpose. The oddly specific 301 was just an off by one quirk of where they drew that line. YouTube smoothed the freeze away long ago, but the skeptical audit underneath never went anywhere. So when someone asks how big sites count views, the real answer is that they do not run a counter at all. They run a pipeline. Events land in a log. A stream processor folds them up, using sketches that trade exactness for kilobytes. A fast store serves the rough number in a millisecond, and a slow batch layer audits it into the truth hours later. 5 stages, 2 paths, and not a single select count anywhere near the hot path. And this is bigger than view counts. Almost every hard scaling problem ends the same way. You want the answer to be exact, and you want it right now, and at a billion of anything, you simply cannot have both. So you choose. You decide where a little wrongness is harmless, and you spend your accuracy where it actually matters, on the money, on the audit, on the things people will check. Get that trade right, and the impossible turns cheap. If this is the kind of systems thinking you enjoy, like and subscribe, because that is exactly what this channel is about. I will see you in the next one.